What if a quiet traveler from deep space were more than a passing light, and instead a gentle turning point for how we think about Mars, about atmospheres, and about patience in science? Tonight we ease into that question with a calm mind and an open notebook, letting verified facts hold steady while possibilities are carefully labelled and set down like smooth stones along a path. This is Science for Sleep, a bedtime exploration where we blend what is known with what might be, using slow, even sentences and an inclusive voice, so your thoughts can drift without hurry as the story unfolds. We will keep our terms plain, our tone level, and our curiosity kind, because restful learning invites a different kind of attention, one that does not race to conclusions but notices how the sky keeps its own pace. We begin with a few anchor points that have become part of the shared vocabulary of stargazing over the last several years. Astronomers have already confirmed that at least 2 visitors from beyond our solar system have crossed our neighborhood, one discovered in 2017 and another in 2019, and those observations opened a new chapter in how we watch the space between the stars. Mars, the rust-colored world that has long carried both scientific interest and quiet myth, holds a very thin atmosphere, made mostly of carbon dioxide, with a surface pressure that is only a small fraction of the average at sea level on Earth. An astronomical unit, which we will use from time to time, is simply the average distance between Earth and the Sun, a helpful yardstick for measuring orbits without juggling unwieldy numbers. These are gentle facts, steady like small lamps on a winter path. Into this calm picture comes a newer visitor that people have nicknamed in many ways, an object that seems to shed gas and dust as sunlight warms its surface and interior, and that approaches the region of space near Mars's orbit. One possibility is that the object is behaving much like other icy bodies that release material as they get closer to the Sun, a natural process that astronomers call outgassing, which is the escape of gases trapped within ice and rock when warmed. A competing view suggests that certain details are unusual enough to deserve special attention, including reports of subtle changes in motion and a chemistry that seems rich in carbon dioxide. It remains uncertain whether those reports will hold after additional observations and updated models, yet the discussion itself has value because it invites better instruments, more transparent data, and patient cross-checks. If you are listening in the dark, perhaps with the faint glow of a bedside clock, it can help to imagine the solar system as a very large, lightly furnished room. The Sun is a quiet heater in the center, the planets are slow-moving chairs and tables, and comets are wandering guests who pass through every so often with a brief shimmer of frost at the edges of their coats. In this room, Mars sits a little farther from the warmth than Earth does, so water there rests mostly as ice, and the air is so thin that liquid water struggles to stay on the surface. When a guest arrives from outside the house altogether, from the long road between stars, we notice, we take notes, we listen to the room. Evidence is limited, but one inference is that the new traveler's composition includes more carbon dioxide than many comets we have measured up close, and that observation has led to thoughtful questions about how such a mix could form. It might be a story of birth conditions in another stellar nursery. It might be a story of processing in space over long spans of time. It might be a mix of both. A minority view holds that if such carbon-rich material were to pass near Mars, it could, in principle, and over long periods, contribute a small amount of gas to a thin atmosphere. That is a modelling exercise, not a forecast, and the scales involved are large, enough to encourage humility. Before we explore the many branches of explanation in later parts, we set a gentle boundary for ourselves. We will distinguish facts from speculation with clear signposts, using simple phrases that keep our footing secure. We will remember that telescopes improve, that measurements mature, and that anomalies often resolve into more ordinary stories once additional light is gathered. We will also allow for the creative use of thought experiments, not as claims about reality, but as ways to test our tools, to ask what kind of data would be needed to support an unusual idea, and to notice where current observations fall short of that standard. In other words, we will move slowly, kindly, and with method. Think of the sky as a shared library. Each object that drifts across our view is a page written in the language of gravity, sunlight, and time. When people speak about changes in a traveler's path, we can translate that into forces and torques, into how gas jets can nudge a body a little to one side, and into how the shape of a rotating object can distribute those nudges unevenly. When people wonder about chemistry, we can translate that into spectra, the faint fingerprints of molecules revealed by the light they absorb or emit, and into how different ices begin to release gases at different temperatures. These translations are soothing because they convert mystery into work, and steady work is friendly to sleep. If the question is whether a single object could swiftly alter Mars in any decisive way, the calm answer is that known physics suggests slow processes spread over long intervals, with many uncertainties. The larger lesson, and the one that makes this a turning point for our thinking rather than a sudden shift in the world itself, is that every well-observed visitor helps us refine our understanding of how materials move and change under the quiet governance of sunlight and distance. One possibility is that this event will lead to improved thermal models of icy bodies at intermediate distances from the Sun, which would help us interpret a variety of future discoveries. A competing view suggests that the conversation will widen to include careful ethical questions about environmental stewardship beyond Earth, even when no intervention is planned, because reflecting on responsibilities can begin long before any action is possible. For tonight, we treat the traveler as an invitation to watch together. We will mark what we can verify, keep possibilities in a clearly labeled basket, and let the presence of uncertainty be a comfort rather than a cause for strain. Humans have always looked up and found both wonder and order, and the rhythm of that looking has its own way of steadying the breath. As we move into the next part, we will gather a small bundle of reliable facts and define a few terms that will make the rest of our journey smoother, like laying out a soft map before a leisurely walk. For now, let the idea rest like a book placed gently on a bedside table. A traveler approaches the wide orbit of Mars. We are watching with patient instruments and open minds. The night is unhurried. So are we. An interstellar visitor is simply an object whose path through space is not bound to our sun, and we know such visitors exist because astronomers have already measured 2 of them with shared effort and careful instruments. In the autumn of 2017, observers detected a fast-moving body, now widely known as the first confirmed interstellar object to pass near the Sun, and in late 2019 a second, more comet-like visitor was found with a coma and tail that matched expectations for icy material warmed by sunlight. These were turning points, not because they changed the solar system, but because they showed that the quiet space between stars is not empty of travelers and that our surveys are now sensitive enough to catch a few when they pass through. As we speak about distances, it helps to define a simple yardstick. An astronomical unit is the average distance between Earth and the Sun, and it allows us to talk about orbits with gentle numbers rather than long strings of digits. Earth lives near 1 astronomical unit from the Sun, while Mars keeps its path farther out at about 1.5 astronomical units, receiving less warmth and holding on to thinner air. When you hear someone say that a comet becomes active at a certain number of astronomical units, they mean that sunlight at that distance has become sufficient to warm surface or buried ices so that gases can begin to escape. A second useful term is outgassing, a plain word for a quiet process in which gases trapped in ice or rock are released as temperature rises. Outgassing can change how a small body moves, not by magic, but by the physics of reaction forces, as escaping jets of gas create gentle thrusts that accumulate over time. In the language of orbit fitting, these are called non-gravitational accelerations, and they can be modeled and measured when observers have enough positions over enough days and weeks. To make sense of what materials are present, astronomers use spectroscopy, which is the study of how matter absorbs and emits light at specific wavelengths. Each molecule has a pattern, a kind of fingerprint, that allows researchers to say with care what might be present in a plume or coma. When a team reports that carbon dioxide appears abundant or that another gas is prominent, they are reading patterns in the light and fitting models that translate those patterns into likely abundances. These models are improved as more data arrive and as instruments are calibrated against known sources. Now we let our attention rest gently on Mars, a rust-toned world that is familiar from photographs and maps yet still new to our senses every time we look again. The air on Mars is thin, with a surface pressure that is a small fraction of the average at sea level on Earth, and it is composed mostly of carbon dioxide, with a smaller share of nitrogen, argon, and trace gases. Daytime temperatures can climb near the freezing point in some seasons and places, but the mean value is far below, and the planet owns broad polar caps made of carbon dioxide, ice, and water ice that advance and retreat with the seasons. Gravity at the surface is a little more than a third of Earth's, and the escape speed is low enough that light gases can be lost to space over long timescales. When people describe dust storms on Mars, they are speaking about winds that can lift fine particles high into the atmosphere, sometimes growing from regional events into planet-spanning veils. These storms filter sunlight and change surface temperatures, and they are observed by orbiters and rovers that send back regular reports. Over years of missions, we have learned to read the seasons of Mars as a rhythm of frost, dust, and light, and that rhythm creates a calm frame for interpreting any future changes with patience. Because this series is meant to be restful, we will keep numbers approximate unless we are citing well-known constants, and we will lean on shared references from space agencies, museums, and textbooks. If you are comfortable doing so, you are welcome to share your listening location or local time as a quiet note of togetherness, and if not, simply notice the breath and let the sky feel wide. The important thing is that we hold the same vocabulary as we proceed, so the story remains clear and gentle. A helpful concept in thinking about warming is albedo, which is the fraction of light a surface reflects. Bright ice reflects much of the sunlight that reaches it, while darker rock absorbs more. On a small body, the patchwork of darker and lighter areas can create uneven heating, and that in turn can guide where outgassing begins and how it changes over a rotation. Over many rotations, these small effects can give a traveler a slightly different path than gravity alone would predict, and careful teams take that into account when forecasting positions for follow-up observations. When we hear that a visitor is approaching the region of space near the orbit of Mars, it does not mean a collision or even a close pass by the planet itself. It means that the distance from the Sun at closest approach is somewhat similar to the average distance of Mars, and in orbital terms, that is a way of placing the object on a solar system map. The geometry of that approach, the inclination of the path with respect to the planetary plane, and the timing of the pass all matter for interpreting what we might see from Earth and from spacecraft. A final definition for tonight is perihelion, which is the point in an orbit that is closest to the Sunday. Many comets become more active as they approach perihelion and then calm as they move away, though the details depend on composition, structure, and the history of heating and cooling cycles. When a team gives an expected date for perihelion, it allows planners to coordinate observations so that telescopes, spectrographs, and imagers can gather the most informative data with the least waste of time and energy. One possibility is that the current traveler will settle into the growing catalogue of measured comets and interstellar objects as another careful case study, adding to our understanding of how ice, dust, and light interact across a range of distances. A competing view suggests that the object could remain interesting because of unusual chemistry or motion, inviting more sustained attention and better models. It remains uncertain whether early reports of anomalies will persist as data improve, and that uncertainty is a friendly place in science because it points directly to the next observations we should make and the instruments we should refine. For now, the fact pack is simple and kind to the mind. We have seen interstellar visitors before. We have a shared yardstick for distance. We know what outgassing is and how spectra help us read composition. We hold a plain picture of Mars as a cold, thin-aired world with seasons of dust and frost. These are steady stones in the path. In the next part, we will step from them toward the pair of curiosities that sparked renewed debate, keeping our pace even and our language calm, so the night can continue to do its work of rest. We begin with motion, because in the language of the sky, motion is the first sentence everything writes. Astronomers fit the paths of small bodies by watching where they appear against the stars, night after night, and then asking a patient question about how gravity alone should carry them. Most visitors follow that expectation well enough that the residuals, those tiny differences between predicted positions and measured positions, scatter around zero in a way that feels ordinary. Every so often, though, the pattern asks for a second look. One possibility is that gentle jets of gas, released as sunlight warms a rotating surface, are adding a subtle push that shifts the path by an amount that is small but measurable. This is called a non-gravitational acceleration, and it has been seen in many comets whose outgassing behaves like tiny thrusters that fire in rhythm with the day and night of the spinning nucleus. A competing view suggests that the pattern of shifts looks more coordinated than those natural torques usually produce, raising the idea that we might be seeing a mix of thermal effects, uneven surfaces, and evolving vents that together create an apparent steering. It remains uncertain whether the reported changes will persist, as additional data smooth the early scatter and as observers add measurements from different longitudes and instruments. Often the first weeks of orbit fitting carry more uncertainty than later months, and what seems unusual in a short arc settles into the ordinary once the curve is extended. For now, the responsible posture is to hold the motion anomaly as a gentle question and to let it guide requests for more precise astrometry, better handling of solar radiation pressure, and careful modeling of how outgassing geometry shifts over time. The second curiosity is chemical, and it comes from how light tells us what is present in the gas surrounding a small body. Spectroscopy, defined simply, is the practice of spreading light into its component colors and looking for faint patterns that match the fingerprints of specific molecules. When teams report that carbon dioxide appears abundant relative to water or other species, they are reading those patterns and translating them through models that connect line strengths and temperatures to likely abundances. Evidence is limited, but one inference is that this traveler formed in a region where carbon-rich ices condensed in greater quantity, or that it has been processed by radiation and time in ways that favor carbon dioxide release when warmed. A minority view holds that the apparent abundance might reflect how the gas is being sampled by our instruments, with geometry, dust content, and temperature gradients convolving into ratios that look unusual at first glance. To hold both curiosities at once, it helps to picture a modestly sized dark object with patches of brighter frost, turning slowly as it falls inward on a long arc. On the sunlit side, shallow layers warm and release trapped gases. On the night side, they chill and quiet. If there is a fresh vent near a ridge or a depression, the escaping gas leaves in a narrow jet that can act like a breath against a sail, giving a small nudge that repeats with every rotation. Over days and weeks, those nudges integrate into a path that is not exactly what gravity alone would draw. One possibility is that the orientation of the spin axis slowly changes as vents open and close, which would shift the direction of the accumulated push and create the impression of a planned adjustment when the underlying cause is simply geology waking up to sunlight. A competing view suggests that the motion and the chemistry, taken together, deserve an expanded toolkit. That might mean more sensitive spectroscopy across a wider range of wavelengths to separate overlapping lines, or thermal infrared measurements that can estimate surface temperatures and help model how deep the heating penetrates. It may also mean coordinated campaigns that pair small professional telescopes with larger facilities, so that the object is watched often enough to capture short-term variability, as well as long-term trends. It remains uncertain whether the carbon dioxide signal will stay high as the traveler approaches greater warmth, since different ices turn on at different distances, and the balance can shift with time. Patience is the instrument that will matter most. There is a quieter layer beneath these curiosities that connects to Mars by way of context rather than drama. Mars orbits at a distance where temperatures are lower and sunlight weaker than on Earth, and the planet carries an atmosphere so thin that even modest additions and losses over long spans can matter to its climate history. One possibility is that interplanetary and interstellar visitors have, over the ages, contributed tiny amounts of gas and dust that participate in that slow balance. A competing view suggests that such contributions are negligible compared with the planet's own internal cycles, with volcanic outgassing and atmospheric escape to space doing most of the long-term work. It remains uncertain whether any single visitor could produce a measurable difference, and responsible discussions tend to keep the focus on timescales of many thousands to millions of years when considering cumulative effects. For listeners settling toward rest, the most helpful frame is not a contest but a map. On one side of the map, we place the motion anomaly, which may be explained by a combination of rotation, uneven heating, and jets that tug in changing directions. On the other side, we place the chemistry note, a carbon-rich signature that might tell a story about birthplace or processing history, or might soften into the ordinary once more data are gathered. Between them runs a path of method: gather more positions, Collect more spectra, compare models with observations, revise gently, let the object itself set the tempo. Evidence is limited, but one inference is that the pair of curiosities will refine how we think about volatile rich bodies at distances where sunlight is weak, yet not absent, a regime where subtle physics becomes important. A minority view holds that the pair could point to categories of objects we have not yet catalogued well, with different families defined by chemistry, porosity, and spin history. Both views can be explored without hurry. Both invite better instruments that will help with the next traveler and the next after that, because the learning accumulates even when the anomalies resolve. If your eyes feel heavy, this is a good moment to let them close and to imagine the solar system as a wide, quiet field beneath a winter sky. A small shape moves across that field with a whisper of gas trailing behind. Its motion is a sentence we are still learning to read. Its chemistry is a hint about places we have not visited. The field is patient. The sky is patient. We can be patient too. We consider first the gentlest explanation for unusual activity far from the sun. The idea that ordinary comet physics can be a little more resourceful than we remember when we picture only bright, close-in tails. Sunlight weakens with distance, yet it does not vanish, and even a modest warming can wake materials that store energy in subtle ways. One possibility is that the surface and near subsurface of a dark, porous body hold ices that respond to slow heating with delayed release. A process guided by the balance between how quickly a layer gains warmth and how slowly that warmth sinks inward. When the topmost grains heat during a long day, a thin film of gas may seep through pores and cracks, and as the object rotates into night, the flow quiets, leaving stresses that build again at the next sunrise. Over many rotations, this cycle can lift dust, open microfractures, and produce faint jets that add up to a measured, non-gravitational nudge. To follow this calmly, we define two helpful ideas. Thermal inertia is the measure of how resistant a material is to changes in temperature, and a surface with low thermal inertia can swing from cold to warm and back again over a single rotation. Amorphous ice is a disordered form of water ice that can trap other molecules within its structure, and when it slowly reorganizes into a more ordered form under heating, those trapped gases can be freed. It remains uncertain whether any specific traveler carries large amounts of amorphous ice, yet the physics is well studied in laboratory settings and in models of outer solar system bodies. Under gentle heating, the release does not need to be dramatic to matter. A weak, steady flow can guide tiny grains off the surface and can impart a small, persistent thrust. A competing view suggests that dust mantles can either suppress or amplify such activity depending on their texture. If a crust becomes too compact, gas struggles to escape and pressure builds beneath, leading to sporadic venting when a crack opens. If the mantle is porous, gas percolates through it like air through a sponge and can carry micron-sized grains with it, creating a soft veil rather than a sharp jet. Evidence is limited, but one inference is that changes in rotation can slowly rearrange how these mantles behave, because sunlight falls at new angles and the daily warm spot marches across ridges and hollows. That slow rearrangement can produce a pattern of thrusts that looks coordinated from a distance without requiring anything beyond natural geology and sunlight. There is also the quiet work of energy stored not as heat, but as light-driven chemistry. On dark surfaces laced with simple organics, ultraviolet photons can break bonds and set up reactions that release small molecules at low rates. This photodesorption, a long word for the gentle removal of molecules by light, does not demand high temperatures, and over weeks or months, it can be a measurable source of gas. One possibility is that a mix of weak heating, photodesorption, and the mechanical breathing of the surface produces the steady glow we interpret as activity at distances where traditional sublimation alone would be slow. It remains uncertain whether this combination can account for every reported case, yet it is a tool worth keeping ready as observations improve. Electrostatic forces may play a supporting part. When sunlight and the solar wind charge grains differently, fine dust can experience lift in low-gravity environments, a process tested on the Moon and contemplated for small bodies with thin atmospheres or none. On a small traveler with patchy charging across day and night boundaries, dust could loosen and become easier for even a faint gas flow to carry away. A minority view holds that this mechanism, combined with slow seepage of gas, could explain early hazes that resemble comey at distances where direct sublimation of common ices would be weak. Careful measurements of grain sizes and speed would help constrain this idea, and those are challenging data to gather from far away, which is why it remains an open question. We can also think about the geometry of how sunlight reaches interior pockets. If a small depression opens toward the sun at a favorable angle, it can act like a shallow cup that collects light and warms efficiently even when overall illumination is scarce. Inside that cup, trapped gases can find a pathway outward, and as the traveler rotates, the cup spends part of each day in shade and part in light, creating a clock-like rhythm to the outflow. One possibility is that a few such features on a rotating body, each with its own timing, could create a pattern of tiny thrusts that looks from Earth like a smooth adjustment to the path. That appearance would soften as we collect longer arcs of data and see the small variations average out. We should hold in mind seasonal effects too. Even a visitor on a one-time pass has a kind of season as it approaches the sun, with the hemisphere tilted toward the light, receiving more warming over a span of weeks. If the spin axis is inclined, the band of most intense heating will migrate with time, waking one set of vents and then another. It remains uncertain whether the axis orientation for any specific traveler is known well enough early on to connect detailed changes in motion to changing seasons, yet the principle helps frame our expectations. What seems like a sudden change may be the natural handoff from one sunlit slope to the next. In all of these natural explanations, the key is not a single strong effect but the harmony of many quiet ones. Small gas flows add small pushes. Microfractures open and close. Dust either masks or reveals warmer layers. Electrostatic lift helps loosen grains that would otherwise cling. Photons do slow chemistry on surfaces that never fully sleep. Over distance and time, these add up to activity that is real yet gentle, and motion changes that are measurable yet small. One possibility is that the object's composition favors carbon-bearing ices that awaken earlier than water, so the first weeks of increased activity show a carbon-rich signature. A competing view suggests that what we see is shaped by the wavelengths we observe, the angles at which we watch, and the scattering behavior of dust, which can bias our sense of abundance until a wider set of measurements arrives. It remains uncertain whether the current traveler will become a textbook example of long-distance activity or will settle into the familiar once its closest pass is behind it. Either outcome is useful. If the activity proves persistent at greater distances than usual, thermal models of porous, mixed ices can be tuned to match the observations, improving our understanding of small bodies formed in cold regions. If the activity recedes into the ordinary, we will have tested our assumptions and calibrated our instruments, which is how steady progress is made. As you rest, picture a small dark object turning in slow sunlight, exhaling just enough to feel a whisper against its own surface. Nothing is hurried, nothing is loud. Yet over many rotations, the whisper draws a line through space that our telescopes can trace. Natural physics, at long distances, is not dramatic, but it is patient and capable, and that patience is its own kind of wonder. In the next part, we will consider a nearby branch of thought that looks at hidden jets from very volatile ices and how geometry can make them look like steering, keeping the same even pace and the same gentle care with what we claim and what we only imagine. We begin with a calm definition. When astronomers speak of supervolatiles, they mean substances that vaporize at very low temperatures compared with water. Carbon monoxide and carbon dioxide are two common examples in small bodies, along with a few other light molecules that can become gas under faint sunlight far from the inner system. One possibility is that beneath a traveler's darker crust, there are pockets where these supervolatiles linger in porous pathways, kept cold by shade and low thermal conductivity, until a change in illumination grants them just enough energy to escape. The flow that follows can be narrow, almost like a fine nozzle, and if it emerges from one patch more strongly than from another, the whole body can feel a gentle push toward the opposite side. Dust mantles influence this story in two different ways that are worth separating. A compact, insulating mantle can trap gas beneath it, leading to cycles of pressure buildup and release when a crack opens, and then reseals with fallen grains. A loose, porous mantle acts more like a sieve, allowing gas to percolate through and carrying fine dust with it so that the jet becomes a soft fan rather than a sharp stream. A competing view suggests that mantles do both over time, starting loose when activity first wakes and growing tighter as particles sinter together under repeated warming and cooling. It remains uncertain whether any single visitor follows this sequence in a simple way, yet the general picture explains why jets can brighten and fade in a rhythm that can mimic intent. Spin matters, and so does sunlight. If the axis of rotation tilts so that one hemisphere enjoys longer, lower-angle light, then vents on that side receive a steady, modest input of energy that never climbs high but never quite disappears. Imagine a ridge with a shallow south-facing slope and a sharper north-facing drop. The shallow side warms through most of a long afternoon, while the steep side sees brief, direct light and then returns to shade. Evidence is limited, but one inference is that vents perched on those different faces will produce outflows with different daily clocks. When you integrate those clocks over many turns, the net effect can be a slow drift of the path that is strongest when a particular face is near the sun and weakest when the spin brings it away. Geometry adds another layer. A hollow with walls that partly surround a vent can act like a natural collimator, narrowing the escaping flow and making the thrust more directionally efficient than a broad open patch would be. A minority view holds that a small number of such features, if placed fortuitously on a rotating body, could create an apparent two-step pattern in the motion that looks like a course adjustment when plotted over short spans. Extend the observations and the steps smooth into a curve, but early arcs can suggest decisions that are better explained by topography and sunlight. Composition is not only about which molecules are present, but also about how they are mixed. Grains that hold carbon monoxide or carbon dioxide ices within pores can be scattered through a matrix of more refractive materials, so that heating does not spread evenly. One possibility is that microscale differences in thermal conductivity cause certain clusters to warm just enough to release gas, while neighbors remain quiet, leading to a speckled pattern of activity across the surface. As the traveler rotates, those speckles sweep through light and shadow and add tiny thrusts that average into a measurable bias over days. A competing view suggests that evolving fractures carve real vents that persist for a while, then clog with fallback dust, then reopen elsewhere. So the thrust vector wanders, not because of changing sunlight alone, but because the plumbing itself is alive. We can listen for these processes in the light. Photometry, the careful tracking of brightness over time, can reveal periodicities tied to rotation, and sudden small changes in brightness can hint at jets turning on and off as vents move into day. Spectroscopy can tell us when a gas like carbon monoxide becomes more prominent, and thermal infrared measurements can estimate surface temperatures that help calibrate how deep the heating penetrates. It remains uncertain whether the current traveler will yield light curves clean enough to time motion changes to specific jet timings, but the method is sound and has been used on other comets to connect behavior with spin and shape. There is a gentle dynamical concept called the rocket effect that brings these ideas together. Each molecule that escapes at a certain speed carries momentum, and the reaction pushes the nucleus in the opposite direction. The thrust is small, but small is not the same as negligible when it operates for weeks. If jets are asymmetric, the cumulative push can offset part of the gravitational pull and shift the path slightly from what a purely gravitational model would predict. One possibility is that the jet pattern evolves with season on the object, so the thrust direction rotates slowly in space, drawing a path that curves a bit more in one interval than in another. A competing view suggests that if 2 or 3 dominant vents have different lifetimes, we may watch the thrust vector jump modestly as one shuts down and another takes over. Dust also feeds back on sunlight. Fresh dust can brighten a region, raising reflectivity and reducing local heating, while darker fallback can lower reflectivity and increase heating, creating a self-adjusting cycle. It remains uncertain whether this albedo feedback is strong enough on small bodies to drive large changes in outgassing, yet it illustrates why surfaces can evolve toward a balance where a once dominant vent quiets and a new, darker patch awakens. Over the span of an apparition, that migration can imprint itself on the orbit solution as a sequence of small, natural adjustments. Hidden jets have signatures. High-resolution images of comets within the inner solar system sometimes show narrow structures in the coma, fans and plumes that correlate with rotation phases. For a distant traveler that remains a point of light in most telescopes, we rely instead on the combination of brightness changes, spectral lines, and precise positions. Evidence is limited, but one inference is that, if position residuals repeat with the rotation period inferred from brightness variations, jets are a strong candidate. If the residuals drift more smoothly without clear periodicities, deeper thermal processes or geometry changes may be carrying more of the story. All of this matters because it teaches us how to read faint, slow physics without rushing to larger claims. Supervolatiles offer a natural way to create activity at distances where water is quiet. Dust mantles regulate that activity, sometimes bottling it up, sometimes letting it flow, spin and shape, decide where sunlight lingers, and how the escaping gas is directed. The path we measure with telescopes is the sum of these gentle contributions. One possibility is that by gathering a longer arc of observations, the early impression of steering will soften into a pattern we have seen before in other comets, fitted by models that include jet-driven forces. A competing view suggests that even with these tools, some features will remain puzzling, pointing us to improve detectors, extend wavelength coverage, and coordinate more observers across more nights so that we miss fewer quiet changes. If you are resting with eyes closed, picture a small fountain in a moonlit garden, its streams angled by the shape of the stone bowl and the breeze. The streams are thin, the motion slow, yet over time, the water carves a path that is plain to see in the morning. Hidden jets on a dark traveler work in a similar register. There is no hurry, only persistence. As we move to the next part, we will trace a neighboring idea, in which the traveler is a fragment from a carbon-rich parent body, and we will keep the same gentle separation between what we can measure and what we only entertain as a possibility. When researchers speak of carbon-rich parent bodies, they often point to families of small worlds that formed in colder regions and kept a generous inventory of carbon-bearing materials alongside various ices and minerals. In meteorite collections on Earth, this family is represented by carbonaceous chondrites, rocks that are dark, porous, and laced with organic compounds and hydrated minerals. In the outer main belt and beyond, astronomers also observe very dark asteroids with rusty red spectral slopes, sometimes called D-type or P-type, whose surfaces absorb rather than reflect much of the sunlight that reaches them. One possibility is that our visitor began as part of such a body, either within our system long ago or around another star, and that a collision or slow tidal stress fractured it into pieces that drifted on new paths. Fragments inherit more than composition, they inherit structure. Many of these small pieces are thought to be rubble piles rather than solid blocks, meaning they are gentle assemblies of pebbles and dust held together by gravity and weak cohesion. In a rubble pile, pores and voids create pathways for heat to travel slowly and for gases to move when warmed. A dark, porous fragment with carbon-bearing ices can begin releasing carbon dioxide at distances where water would still be quiet, because those molecules are more volatile, and because the internal plumbing of pores lets the gas reach the surface without needing large cracks. Evidence is limited, but one inference is that such a fragment could show a carbon-rich coma early in its approach, and that this appearance would be a natural outcome of its ancestry, rather than a sign of anything unusual. Spectroscopy can hint at family ties when direct sampling is not possible. A spectrum that rises gently toward longer wavelengths with a low overall reflectivity suggests a dark, carbonaceous surface. The presence of certain absorption features can point toward organics or minerals altered by water in the past, though these signatures can be subtle at the distances where interstellar visitors are typically observed. It remains uncertain whether current data for the traveler are precise enough to tie it cleanly to a known asteroid or meteorite class, yet the idea of a carbon-rich fragment stays reasonable while instruments gather more light. One possibility is that as the object warms, the balance of gases in its coma will shift and reveal a broader suite of molecules, helping to refine its match to known families. Parent bodies do not all live quiet lives. Gentle collisions can loft surface material into space, and rarer, energetic impacts can disrupt a small world entirely, sending a cloud of fragments onto new orbits. A competing view suggests that thermal stresses, alone, without dramatic impacts, might fracture a body over time as it cycles between cold and warmer seasons, especially if it has traveled near stars before. These processes are slow and unhurried at the scales that matter for sleep, but over long spans they can populate space with pieces that carry distinctive chemistries. It remains uncertain whether the traveler's history involved a catastrophic disruption or a more gradual shedding, and distinguishing between those histories from afar is challenging. Porosity carries consequences for motion. A highly porous fragment has low density, which means that the same gentle outgassing can produce a slightly larger acceleration than it would on a denser body. The surface texture also influences how sunlight is absorbed and re-emitted as heat, a process called thermal re-radiation that can create tiny forces over time. One possibility is that the observed path deviations are a harmonious sum of gas thrust and thermal effects shaped by a dark, low-density surface inherited from a carbon-rich parent. A competing view suggests that even if the traveler is carbonaceous, the measured motion changes may still require more active jets than porosity and thermal emission alone can provide. Returning us to the interplay of vents and geometry discussed earlier, water can leave traces even when water ice is no longer present. Many carbonaceous meteorites show minerals that formed when liquid water interacted with rock, a sign that their parent bodies once hosted warmth from radioactive decay or long-stored heat. If our traveler shares that ancestry, it may carry minerals that record a history of mild alteration, and those minerals can change how the surface holds and releases heat today. It remains uncertain whether remote spectra at current distances can detect such mineral fingerprints. Yet laboratory work with meteorites and analog materials helps model how a surface with these traits would behave under sunlight. One possibility is that the combination of dark organics and altered minerals creates the early onset of activity that observers report. The carbon dioxide itself invites a gentle note on sources. In a carbon-rich body, carbon dioxide can exist as ice in pores, as trapped molecules within amorphous water ice, and as a product of chemistry in irradiated organics near the surface. When warming begins, each source awakens on its own schedule, and the earliest signals can be biased toward the species with the lowest activation energy for release. A competing view suggests that what appears to be an abundance may partly reflect how dust and gas scatter and absorb light at the wavelengths used, which can make one molecule seem more prominent until additional bands are observed. It remains uncertain whether calibration across instruments will reconcile those views quickly, so a calm patience remains wise. If the traveler is a shard from a larger carbonaceous body, there are gentle clues we can watch for as it nears and recedes. Light curves that reflect an irregular shape can hint at a fragment rather than a rounded block. Color trends that remain consistently dark across multiple filters support a carbon-rich surface. Changes in gas species as the sun warms deeper layers can outline the stack of volatiles, from more volatile to less volatile, in a way that maps to known compositions from meteorites and space missions. Evidence is limited, but one inference is that a late appearance of water lines after an early carbon dioxide signal would fit the story of a layered, porous fragment waking from the outside in. There is a quiet comfort in how this branch needs no extraordinary assumptions. Worlds collide or crack, pieces drift. Some pieces are dark and porous, rich in carbon and readily warmed. When they approach a star, the gentlest gases stir first, and the path they trace through space carries the signatures of their ancestry. One possibility is that the current traveler will teach us more about fragment strength, about how rubble holds together under rotation, and about how porosity shapes both brightness and motion. A competing view suggests that even if the fragment picture is broadly correct, the details of chemistry and thrust will still surprise us, nudging models toward greater nuance rather than overturning them. If you are listening with eyes closed, imagine a quiet field of small dark stones warmed by afternoon sun, each stone holding a bit of frost within and releasing a faint breath as the day deepens. None of the breaths is strong, and yet each tells a story about what the stone is made of, and how it came to rest where it island. Our traveller may be such a stone on a grander stage, a fragment whose calm exhalations and soft reflectance whisper of a carbon-rich past. In the next part, we will turn to the idea that gravity itself, through a sequence of distant encounters and gentle pushes from escaping gases, can reshape a path in ways that look unusual at first glance, keeping the same even cadence and the same clear separation between measurements and possibilities. Gravity is the most patient sculptor in the sky. Every object with mass attracts every other, and for small bodies moving through the solar system, the collective pull of the sun and planets sketches a path that would be entirely predictable if nothing else intervened. In practice, two families of influences share the stage. There are gravitational encounters, which are the gentle passing interactions between a traveler and a distant planet that alter the speed or direction by a small but calculable amount. And there are non-gravitational torques, the tiny thrusts produced when sunlight warms ices and releases gas in uneven patterns across a rotating surface. Together, they can draw a line through space that departs slightly from a purely gravitational prediction, while still remaining a natural outcome of known physics. A distant gravitational encounter is not a dramatic flyby. Think instead of a slow exchange of momentum across a long span. When a traveler passes tens of millions of kilometers from a planet, the planet's gravity can either add a little energy or subtract a little, depending on the geometry of the approach. The change is small, yet small is meaningful when we are fitting precise positions across months. One possibility is that an early orbital solution, based on a short arc of data, may not include the full effect of such a distant tug. And as more measurements arrive, the solution will converge to a path that naturally incorporates that encounter. A competing view suggests that if the residuals remain even after those encounters are modeled, the remaining differences are better explained by outgassing forces acting in concert with gravity. Non-gravitational torques enter the picture when a surface warms and exhales. Gas leaves predominantly from the sunlit side, and because the body is rotating, the direction of that push changes through the day. If vents are concentrated on one hemisphere, or if the spin axis is tilted, the time-averaged result becomes a steady thrust in a particular direction. It remains uncertain whether the present traveler has a spin state and vent distribution that produce a large net effect. Yet the principle has been observed in many comets and is included routinely in precise orbit models. Evidence is limited, but one inference is that adding a simple 3-parameter outgassing model often absorbs residuals that initially looked like unmodeled gravity. When gravitational and outgassing effects operate together, their signatures can partially overlap. A distant planetary tug can change the timing of where the traveler is on its path, while steady gas thrust can bend that path gently over weeks. One possibility is that observers interpret early curvature as evidence for an encounter that never happened, when in fact, outgassing did most of the work. A competing view suggests that a barely perceptible encounter set the stage, nudging the object into a slightly different geometry where sunlight reached vents more efficiently, amplifying non-gravitational forces that would otherwise have remained small. It remains uncertain whether we can always separate the two cleanly with data taken from Earth alone, which is why coordinated campaigns and multiple wavelengths help. The solar wind and sunlight pressure also contribute, though they usually play supporting roles. Photons carry momentum, and when light reflects or is absorbed and re-emitted by a small, low-mass body, the recoil imparts a minute push called radiation pressure. Over long stretches, this can shift the path perceptibly. Dust in the coma increases the cross-section for sunlight, which can enhance the effect. One possibility is that a dusty outburst temporarily increased the radiation pressure contribution, which then softened as the coma thinned, leaving a transient signature in the residuals. A competing view suggests that radiation pressure remains too small for the current case, and that gas thrust plus distant gravitational geometry suffice. An instructive tool for this quiet choreography is the concept of resonant returns. Picture a traveler and a planet that meet at one point in space, separated by millions of kilometers, and then meet again years later because their orbital periods fall into a near ratio. The earlier encounter, even if weak, sets the phase for the next, and the next can be slightly closer or slightly farther depending on the first. Evidence is limited, but one inference is that a chain of barely noticeable encounters can accumulate into a measurable effect on timing and position by the time we begin our intensive observations, and if we only fit the late arc, we may misattribute the result to current physics alone. It remains uncertain whether resonant returns matter for a one-time interstellar visitor, yet the broader lesson holds. History matters in orbital dynamics. There is a restful way to picture the mathematics. Imagine a narrow river with a gentle current bending around stones. Gravity is the current that carries everything forward. A distant planetary encounter is a slow bend in the bank that slightly changes the water's direction. Outgassing is a set of small paddles occasionally dipped into the water on one side of the boat. Each paddle stroke is weak, but the strokes repeat with the rhythm of rotation and season. Over time, the boat ends up a little to the left of where the water alone would have carried it, and if a bend in the river came just before the paddling began, the final position reflects both influences. No single moment is decisive. The sum, island. To test these ideas, astronomers build models that include parameters for gas thrust, often tied to a function of distance from the Sun, and look for improvements in how the computed path matches the measured positions. If the fit improves and the parameters remain physically plausible, confidence grows that natural forces are sufficient. One possibility is that thermal infrared observations, which estimate surface temperatures, can anchor those parameters by telling us when and where warming should be strongest. A competing view suggests that we should remain cautious, because different combinations of parameters can fit the same data when the arc is short, and additional observations will be needed to break degeneracies. It remains uncertain whether such degeneracies have played a role in early interpretations for the present traveler. Mars enters this discussion as context, rather than as a target. When we hear that a visitor's closest approach to the Sun lies near the distance of Mars, it simply means the traveler reaches maximum warmth on an orbit that sweeps past the same broad annulus where Mars spends its time. The chance geometry for a true close pass with the planet itself is usually small. One possibility is that the traveler's gas thrust could shift the timing enough to make a distant encounter with Mars marginally closer or farther than a gravity-only model would have predicted, without implying any interaction of consequence. A competing view suggests that such differences are within normal modeling uncertainties, and that the focus should remain on improving gas and radiation terms rather than invoking specific planetary effects. Amid these calm possibilities, we hold a steady disclaimer. The motion we attribute to non-gravitational physics must always be tempered by new measurements, cross-checked by independent teams, and tested against alternative explanations that remain within established science. Claims that reach beyond this method should be framed as thought experiments, clearly labelled and set aside from the observational core. The sky is generous to those who wait. Curves that seemed puzzling in the first weeks often settle into clarity by the third month. If you are resting with your eyes closed, imagine the traveller as a small leaf moving on a wide stream. The stream bends gently because of the shape of the shore. Sunlight touches one edge of the leaf more than the other, and a faint curl of vapour pushes it slightly sideways. Over the length of a meadow, the path is not exactly where you would have drawn it if you had only traced the current, yet nothing surprising has occurred. Only the sum of small, familiar influences. In the next part, we will pause for a mid-script disclaimer and a brief reset of terms, so that our map stays clear and our pace remains easy. This series rests on a calm promise. We will hold to what can be checked, and we will cradle possibilities in language that keeps them where they belong, as open questions rather than conclusions. Midway through our nighttime walk, we take a brief moment to say clearly what is known, and to remind ourselves what is still unfolding. The sky is generous but not hurried, and patient wording helps both science and sleep. Some anchors feel steady in the hand. Astronomers have observed visitors that came from beyond our sun's family, and those detections changed how surveys scan the sky. Mars is a cold world with thin air dominated by carbon dioxide, a surface pressure that is only a small fraction of Earth's, seasonal frosts, and global dust events that are watched by orbiters and rovers. An astronomical unit is simply the average distance from Earth to the Sun, a yardstick that keeps numbers friendly. Perihelion is the point at which an orbit comes closest to the Sunday. These pieces are not under debate, they are the shared vocabulary of the room we are standing in together. Next come terms that have already appeared and will return gently in the parts ahead. Outgassing is the quiet release of gases when sunlight warms buried ices and trapped molecules find pathways to the surface. Non-gravitational acceleration describes the small changes in motion that arise when those gas flows act like tiny thrusters on a rotating body, adding up over many hours and days. Spectroscopy spreads light into many colors to read the faint fingerprints of particular molecules or minerals, while photometry tracks brightness over time to learn about rotation and activity. Thermal inertia is the tendency of a material to resist temperature change, and albedo is the fraction of light a surface reflects. Supervolatiles are substances, such as carbon monoxide and carbon dioxide, that can vaporize under very modest warming compared with water. Radiation pressure is the minute push from sunlight itself. A resonant return is a rhythm in orbital timing that lets a traveler and a planet come into similar geometries at different epochs, even if they never pass very near. With these ideas set out plainly, later steps will feel more like a stroll than a climb. There is one term that deserves a single, careful sentence of definition because it can carry more weight than a bedtime story should: terraforming, in the way scientists use the word in thought experiments, means large-scale, long-duration efforts to change a planet's environment to become more hospitable for life. It is a hypothetical engineering concept, not a present plan, and its timescales in realistic physics are long, measured in many decades to centuries or more. We will treat the word as a model in the sandbox of ideas, rather than an expectation for action. With language refreshed, we place our disclaimer like a soft bookmark. When we say that an object's path may be shaped by jets of gas, we are staying on the firm ground of many observed comets. When we note that reports of unusual chemistry and motion deserve a second look, we are acknowledging that early measurements can shift as more light is gathered and as models mature. When we explore the thought that a traveler might be a fragment from a carbon-rich parent body, we lean on families of asteroids and meteorites that are well documented, without insisting on a match before the data are strong enough to make one. And when we turn to broader what-ifs that test our tools, we will mark them with careful openers that keep their status clear. One possibility is that the traveler's early carbon-rich signal reflects natural layering in a porous fragment where more volatile ices awaken first. A competing view suggests that the signal may soften as geometry and calibration improve, bringing ratios of gases closer to values seen before. It remains uncertain whether non-gravitational forces alone can account for all reported motion changes, and additional positions over a longer arc will help decide how much thrust the models actually need. Evidence is limited, but one inference is that small features on a rotating surface can collimate escaping gas and mimic the appearance of deliberate steering when plotted over short spans. A minority view holds that distant gravitational nudges, or brief dust outbursts, could also leave signatures in the residuals that fade with time. Each sentence here begins with a signpost, so your mind need not wonder where the ground ends and the open field begins. There is also the human side of method, which can be as soothing as any star map. Observers in many countries share time on instruments and post their measurements to public databases where anyone can examine them. Teams compare fits, swap calibration notes, and revisit assumptions with the respectful persistence that moves science forward. Negative results are recorded because a careful "we did not see this" narrows the path as surely as a successful detection widens it. The pace is slower than the feed of daily headlines, yet that slower pace is the only one that reliably turns hints into knowledge. When you hear that a claim has not yet cleared peer review, it does not mean the claim is wrong. It means the community is doing the steady work of testing it. Because nighttime listening is eased by simple metaphors, keep this one nearby. Think of the solar system as a quiet garden in winter. Some branches stir at the first hint of warmth. Others remain still until the sun is higher. A traveler passes the fence line and leaves a few prints in the frost. From one angle, the prints look close together. From another, they look farther apart. As more tracks appear, the path resolves, and what seemed at first like a sudden turn often becomes the natural arc of a patient walk. Our role is to keep watching without gripping too tightly at the earliest shapes. We close this pause with a reminder about scale. In the realm of realistic physics, single objects do not swiftly transform planets. Small bodies can contribute a little dust or gas. Over long timescales, many small contributions may matter, and models can explore such possibilities without predicting them. The central lesson is humility. Good instruments help, shared data help. Careful language helps most of all, because it keeps our balance when the ground is uneven. As we return to the main path, let your breath match the measured cadence of these ideas. We have reset our terms. We have placed our disclaimer softly at the center. In the parts that follow, we will try on a thought experiment about artificial craft, detection thresholds, then step through broader societal and ethical reflections, always keeping the signposts in place and the tone level. The night is unhurried, the sky is wide, and method is a kind companion. We begin by setting the ground gently. In astronomy, extraordinary claims are welcomed as questions and must be met by extraordinary evidence before they are accepted as conclusions. The sky is not opposed to surprises, yet it asks us to earn them with data that are precise, repeatable, and independently confirmed. One possibility is that by walking through the kinds of signatures a genuine craft would need to display, we can sharpen our instruments and our thinking, even if nature supplies only natural comets and fragments. A competing view suggests that such exercises risk distraction if they are not anchored to real measurements. The balance we aim for tonight is calm and useful, with method at the center. If an object were truly propelled by technology, there are families of observations that could raise confidence step by step. The first step would be motion that cannot be reconciled with gravity, radiation pressure, and gas thrust after a long observing arc and careful modeling. Non-gravitational accelerations from vents usually correlate with sunlight and rotation in predictable ways. It remains uncertain whether early residuals for the current traveler will hold once more positions, thermal estimates, and coma diagnostics are folded into the fit. Evidence is limited, but one inference is that persistent, rotation, independent changes in trajectory would be more distinctive than changes that track solar distance or inferred vent timing. A second step would involve energy. Known propulsion leaves traces, whether in waste heat, expanding gases, or electromagnetic emissions. One possibility is to use thermal infrared observations to search for localized warmth that is inconsistent with solar heating and surface properties, accounting for rotation and shadowing. A competing view suggests that a cleverly insulated device might mask waste heat, yet masking itself would create signatures in how the surface re-radiates energy over a rotation. It remains uncertain whether our current instruments, at present distances, can detect such fine deviations, but the path is clear. Measure temperatures. Compare to models constrained by reflectivity and shape. Look for mismatches that persist. Third comes composition. Superheated exhaust, engineered materials, or unusual line ratios in a plume could flag non-natural processes. Spectroscopy can look for molecules that are improbable in cometary chemistry at the measured temperatures, or for ionized species in combinations that suggest controlled reactions. A minority view holds that exotic chemistry might be engineered to mimic natural mixtures. Even then, the mixture would need to match temperature, density, and flow speeds in ways that cohere across independent instruments. Careful multiband campaigns, with cross-calibration between observatories, would be needed to support such a claim. Fourth is morphology. High-resolution imaging near closest approach could reveal geometric features that depart from known cometary forms. Jets normally emerge from irregular patches and produce diffuse fans or spirals tied to rotation. One possibility is that resolved, symmetric structures with angles or repeating modules might hint at manufacture. A competing view suggests that lighting and viewing geometry can trick the eye, and that diffuse dust often creates shapes that feel structured when they are not. It remains uncertain whether we will have the resolution to test morphology this time, yet even a marginally resolved coma can rule in or out simple options, which is valuable. Fifth is repeatable control. A genuine craft might adjust its path in ways that clearly relate to external conditions or internal schedules rather than to heating. For example, a change in vector that occurs during darkness as well as daylight, or an alteration that anticipates a gravitational interaction rather than following it, would be noteworthy. Evidence is limited, but one inference is that a sequence of timed maneuvers, separated from rotation phase and solar distance, would carry more weight than a single deviation. It remains uncertain whether any small body we have tracked shows such signatures once modeling is complete. Another family of tests involves interaction with signals. Radar, if geometry allows, can probe surface structure and spin. Polarization studies can reveal how light scatters from the surface and dust, which constrains texture and particle size. One possibility is that polarization, angles that remain unusually constant across phase angles, might indicate engineered coatings, though rough surfaces can also flatten the response. A competing view suggests that dust-dominated comae often complicate interpretation, so clear tests require clean, well-timed observations near phases when dust is minimal. Data stewardship matters as much as detection. Claims of artificial origin gain credibility when raw and reduced data are shared openly, when independent teams reproduce analyses, and when negative results are logged. It remains uncertain whether every facility observing the current traveler will release data on the same cadence. Yet community experience with transient events shows that shared repositories and standardized formats are both possible and beneficial. One possibility is that this thought experiment will encourage observers to coordinate thermal, spectroscopic, and astrometric measurements so that modeling can be constrained from multiple sides, reducing room for interpretive drift. We should also name two common pitfalls. The first is parameter elasticity, where models with many adjustable terms can fit almost any path if given sufficient freedom. Responsible practice limits parameters to those that have physical meaning and ties them to independent measurements wherever possible. The second is confirmation bias, the human tendency to favor interpretations that match our hopes or fears. A competing view suggests that open pre-registration of analysis plans, where teams specify in advance which tests they will run and which thresholds will count as significant, can keep us grounded. Measured at an easy pace, these practices soothe both science and sleep. Ethics enters gently, even in a thought exercise. If one day an object truly displayed signs of control, telescopes would become not only instruments but also points of contact. Planetary protection principles, usually applied to spacecraft missions, offer a useful template for language and restraint. It remains uncertain whether any practical interaction would be possible at all, yet early reflection keeps both curiosity and respect in balance. One possibility is to commit in advance to non-invasive observation, to avoid actions that might alter the object or its surroundings, and to collaborate widely across cultures so that no single group claims the sky. Against this careful backdrop, we return to the present case with a calm, simple statement. The available evidence still sits within natural categories that we have explored in earlier parts. Non-gravitational forces from outgassing, radiation pressure on dust, and the slow arithmetic of distant gravitational geometry are sufficient tools for explaining most reported behavior once long arcs of data are gathered. The chemistry notes that have sparked interest can be framed within known families of carbon-rich materials and the layered release of volatiles as sunlight reaches deeper levels. It remains uncertain whether any residuals will survive. Improved modeling, and the community is already doing the patient work of fitting, checking, and refining. Thought experiments like this one earn their rest when they give us clearer checklists. Motion that persists beyond gas and light, heat that resists solar accounting, composition that contradicts natural chemistry at measured temperatures, shapes that keep right angles under changing light, maneuvers that ignore day and night, shared data that allow independent confirmation. None of these on its own would be enough. Together, over time, they would begin a new conversation. For now, the night is quiet. We have a traveler that invites better observations and more careful models. We have a method that values restraint, and we have room in our minds for wonder that does not hurry. In the next part, we will use equally gentle arithmetic to consider a modeling exercise about staged deliveries of volatiles to a thin atmosphere, why such ideas attract attention, and why realistic timelines tend to be long and uncertain. Your breath can stay slow, the sky keeps its pace. We start with a simple picture of how air holds warmth. Sunlight arrives at a planet's surface and atmosphere. Some is reflected back to space, and some is absorbed and later re-emitted as infrared radiation. Greenhouse gases, such as carbon dioxide, interact with this outgoing infrared light and can slow its escape, gently lifting average temperatures compared with a bare rock under the same Sunday. On Mars today, the air is thin, mostly carbon dioxide, and the surface pressure is only a small fraction of Earth's. One possibility is that if more gas were present, radiative effects and pressure together could raise temperatures a little, because thicker air both traps more heat and helps reduce the rate at which molecules escape to space. A competing view suggests that the cold, the weak sunlight at Mars's distance, and the many pathways for loss would keep changes modest, unless the amounts added were very large. To estimate scales without strain, we use round numbers. The total mass of the current Martian atmosphere is on the order of tens of quadrillions of kilograms. A typical small comet might carry mass in the range of billions to hundreds of billions of tons, but only a fraction of that is gas, available to stay aloft after dust settles and after interaction with sunlight. It remains uncertain whether any single visitor could add more than a trace relative to the whole, and even a sequence of visitors would need to deliver material reliably over long spans to matter. Evidence is limited, but one inference is that if staged deliveries were ever envisioned, they would resemble a multi-decade or multi-century program, not a single season of change. Another layer is temperature. Greenhouse physics on Mars is not a simple copy of Earth's. The lower gravity and colder air shift where and how carbon dioxide condenses, and the polar caps of carbon dioxide ice breathe seasonally, taking gas out of the air in winter and returning it in spring. One possibility is that adding more gas would partly amplify those natural cycles, thickening the atmosphere in some seasons and thinning it in others, with regional differences that depend on dust and clouds. A competing view suggests that new gas would be countered by stronger condensation at the poles, restoring much of the original balance unless the additions were sustained and substantial. It remains uncertain whether remote delivery alone could outpace these sinks without complementary processes, such as slow release from surface minerals or subsurface ice. Loss to space matters as well. Mars lacks a global magnetic field, and measurements by orbiters show that the solar wind can help strip away lighter constituents over long periods. The heavier carbon dioxide is more durable against this process, but not immune when broken into components by sunlight. One possibility is that a slightly thicker atmosphere could shield itself more effectively by reducing the fractional loss rate. A competing view suggests that escape pathways would simply adjust to the new conditions and continue, changing the balance but not eliminating loss. Either way, loss operates on long timescales, which means any gain measured in years would likely be small compared with the sizes needed for climate shifts. Because listeners are settling toward rest, we keep the arithmetic soft. Suppose a small fraction of an object's mass becomes gas that truly stays in the air rather than falling as frost or dust. Suppose further that a handful of such objects contributed similarly across many years. The integrated addition could still represent only a small percentage of the atmosphere's mass. It remains uncertain whether that percentage would rise above the natural variability Mars already experiences through seasonal polar exchange and dust-driven changes in temperature. If it did, the signal would likely be subtle and distributed unevenly across latitude and season, detectable by careful instruments but not dramatic to the eye. Delivery is also a problem of aim and form. Natural visitors arrive on paths set by gravity and their own gentle outgassing, and their material is spread over large volumes. A minority view holds that if objects were purposefully steered and their release timed near the upper atmosphere, efficiency could improve. Even in that scenario, compression heating, chemistry in sunlight, and the tendency for condensable species to frost onto cold grains would dilute the effect. One possibility is that a staged concept might focus less on a single gas and more on a portfolio, pairing carbon dioxide with species that influence cloud properties or surface albedo. But now the complexity grows, and so do the uncertainties. Mars itself would reply. Dust storms can encircle the globe and alter how sunlight reaches the ground. Thin clouds can change the balance between daytime warming and nighttime cooling. Surface frosts and polar caps respond to changes in light and air in ways that feed back into the whole system. A competing view suggests that these internal dynamics would dominate over any gentle, intermittent additions from occasional visitors, at least until changes reach scales far beyond what a handful of natural objects could deliver. It remains uncertain whether any measurable thickening in the near term would be distinguishable from the normal rhythm of the planet's seasons without a long baseline of careful observations. Ethics belongs in an exercise like this, even when the exercise stays in the realm of models. Planetary protection principles ask us to avoid contamination and to act as careful stewards when dealing with worlds that hold scientific value. One possibility is that reflecting on hypothetical delivery helps us refine those principles and recognize how easily dramatic language can run ahead of measured capability. A competing view suggests that we should devote our planning energy to observation and understanding rather than to intervention, especially where the thresholds for meaningful change are so high and the risks to scientific clarity so real. There is a calmer, practical benefit to the exercise. By tracing what would have to align for a staged delivery to matter, we identify the observations that most help us decide whether natural visitors have any detectable effect at all. We would look for small regional changes in pressure profiles, for shifts in the seasonal breathing of the polar caps, for persistent differences in trace gases that correlate with arrival times, and for radiative signatures that deviate from long-term baselines. Evidence is limited, but one inference is that a carefully built time series from Mars orbiters and landers provides the best chance to see or to rule out such gentle contributions, and that many years of data are the right scale. It is also helpful to mark what this exercise does not do. It does not predict that visitors will change Mars quickly. It does not treat speculative delivery as a current plan or a hidden program. It does not substitute arithmetic for observation. Instead, it turns a popular question into a checklist that science can use, measure, compare, and decide. That stance keeps curiosity intact while letting rest take its place beside it. A final, sleep-friendly picture. Imagine a quiet lake on a cool morning. A few leaves fall and send tiny ripples outward. If you wait with patience, you can see the ripples cross and fade, yet the level of the lake remains almost the same. Mars is the lake. Visitors are the leaves. One possibility is that the ripples tell us something true about how the surface and the air exchange warmth. A competing view suggests that the lesson is simpler, that the lake's own springs and breezes set the story while the leaves only mark the moment. In the parts ahead, we will step from modeling into culture and method, asking how stories about the sky form and why they matter, and we will keep our disclaimers close. Tonight's conclusion is gentle. If staged delivery were ever contemplated, physics points toward long times, small increments, careful ethics, and the primacy of good observations. It remains uncertain whether natural visitors add anything measurable in the near term, and that uncertainty is peaceful. It tells us exactly what to watch, and it lets us sleep while the instruments keep their quiet vigil. Across cultures and centuries, people have looked up at night and made meaning. The constellations are maps of that meaning, a soft record of navigation and myth, of planting calendars and poems, of warnings and blessings given shape by stars. Today, our tools are sharper and our language more precise, yet the human rhythm remains. We meet a new visitor, give it a name to hold it in mind, and then begin to imagine what it might mean. One possibility is that this imagination is a healthy companion to science, encouraging questions that lead to better measurements. A competing view suggests that imagination can outrun evidence, inviting dramatic conclusions that feel vivid, but leave us unsteady when the data grow up and point back to ordinary physics. It remains uncertain whether any single narrative can hold the wide span, from public excitement to careful analysis, which is why many narratives are needed, and why humility in tone is a strength. Media shape these narratives in ways that are easy to feel and useful to name. Headlines compress, and in the compression nuance can slip away. Visuals emphasize motion and color because the eye loves motion and color, while many of the most informative plots in planetary science are steady line graphs and quiet black and white spectra. Evidence is limited, but one inference is that a calm division of roles helps. Outlets that carry the first announcement, museum and university pages that offer gentle explanations, and journals that host the slow, technical work. A minority view holds that platforms can be designed to encourage the cadence of patience, with visual cues that remind readers where speculation begins and ends, much as we do here with simple signposts. The design of our information rooms matters for sleep as much as for science. Psychology also has a place in this quiet room. Human minds are built to notice patterns and to complete them when pieces are missing. That trait helps in daily life, yet it can mislead when uncertainty is high and stakes feel large. One possibility is that reminding ourselves of cognitive habits, such as confirmation bias and the tendency to prefer dramatic explanations, can soften their pull. A competing view suggests that community practices do the heavier lifting, because shared checklists and pre-registered analyses keep teams grounded even when excitement rises. It remains uncertain whether reminders or practices matter more, but together they create a gentle guardrail that lets curiosity wander while keeping conclusions close to measured ground. Ethics enters whenever our attention turns, from watching to interpreting, and from interpreting to proposing actions. Planetary protection, in its modern form, asks us to avoid forward contamination of other worlds and to preserve records of natural processes. One possibility is that this principle extends naturally to our narratives, encouraging language that protects the scientific value of a world by avoiding claims that would be difficult to untangle later. A competing view suggests that ethical reflection should also include how stories affect communities on Earth, especially when extraterrestrial themes blend with hopes or worries about technology, environment, or belonging. Words are part of our ecosystem. Choosing them with care is a form of stewardship. There is a social dimension to wonder that is gentle and good. Amateur observers contribute positions that extend the nightly arc. Students build instruments that join professional networks. Families visit planetariums and carry home a quieter sense of scale that lasts for years. Evidence is limited, but one inference is that the most restful and resilient public understanding comes when institutions invite participation at many levels, with opportunities to learn, to measure, and to share. A minority view holds that bedtime science stories like this one play a modest role by modeling a pace that is careful, inclusive, and kind to uncertainty. In that spirit, if you feel comfortable, you are welcome to share your listening location or local time as a soft note of togetherness, and if not, simply notice your breath and the room that holds you. Both options are equally welcome. Museums and university pages often serve as the bridge between research and rest. They host glossaries, quiet explainer pages, and historical timelines that place new events within long arcs. One possibility is that adding small labels to these resources that clearly mark which items are confirmed and which are active areas of study can help keep speculation from masquerading as fact. A competing view suggests that the best bridge remains conversation. Talks where questions are welcomed without rush, where a presenter pauses to define a term in one careful sentence, and where uncertainty is treated as a friendly companion. It remains uncertain whether digital or in-person formats will carry more of this work in years ahead. Yet the intention is the same. Make room for slow learning. Policy has a seat at the table too, though it should arrive quietly. When reports of unusual objects appear, agencies coordinate observation time, and if any concern about risk were ever warranted, formal processes exist to evaluate it without urgency and tone. One possibility is that publishing simple, transparent checklists for how claims move from early reports to evaluated statements would reduce speculation and build comfort. A competing view suggests that flexibility is necessary because every object brings its own geometry and constraints. It remains uncertain whether a single checklist can serve all cases, yet principles can be public, even when details vary. Share data when possible, welcome independent checks, name uncertainties plainly, and keep comparisons to past events nearby so scale is not lost. Education during moments of sky-wide interest can be both restful and formative. When learners hear a teacher say that a measured motion may reflect gas thrust rather than control, or that a bright signal may soften with calibration, they are not being denied wonder. They are being invited to a more durable kind. Evidence is limited, but one inference is that pairing real plots and spectra with accessible metaphors builds confidence, because learners can see how claims travel from light to conclusion. A minority view holds that we should also teach the art of waiting, the practice of leaving a margin of blank, space in the mind where new data can fit later without friction. Waiting is a skill that helps far beyond astronomy. We return to our standing disclaimer, now framed as an ethic. We speak softly where evidence is thin. We separate the firm from the possible with simple, repeated language. We let uncertainty be a neighbor rather than a stranger. We keep timescales honest, marking how long nature usually takes to make differences we can measure. We remember that a single object, however interesting, is a page and not the whole book. One possibility is that this posture will feel modest. A competing view suggests it is also strong, because it leaves fewer regrets when the next set of measurements arrives. Stories will continue to bloom around the traveler. Some will be playful and harmless. Some will be thoughtful and helpful. A few may be sharp at the edges, making claims that crowd the night with urgency it does not deserve. It remains uncertain whether any narrative can satisfy every listener, but we can all choose what we amplify. We can pass along the explanations that breathe evenly, the plots that show their axes and units, the phrases that keep their feet on measured ground. We can also let a story rest when it tries to rattle the room. As you settle deeper into the quiet, imagine a circle of people beneath a gentle sky, sharing a telescope and a thermos of tea. Someone names a constellation. Someone else writes down a time and a brightness. The group pauses while a satellite glides past, and the visitor they came to see looks much like a star, which is the ordinary way of small, far things. The pause is the heart of the evening. In that pause, wonder and method agree to be patient together. In the next part, we will turn the lens back to science, stepping through a calm set of hypothesis branches that widen the map without raising the voice. Natural jets and spin, porous carbon-rich fragments, layered ices, rotation-driven plumbing, distant gravitational, geometry, radiation, pressure on dust, seasonal surface changes, and measurement artifacts that resolve with time. Each branch will keep the signposts clear, and each will end with a soft reminder of what would help decide among them. For tonight, let the social side of the sky feel simple. Shared care, shared data, shared rest. Branch 1 is natural jets and spin. One possibility is that sunlight wakes patches of volatile ice that vent in narrow streams, and the rotation of the body turns those streams into a time-average thrust that bends the path slightly from a gravity-only line. This sits on well-measured ground, because many comets show non-gravitational accelerations that correlate with distance from the Sun and with inferred rotation periods. What helps decide? Precise astrometry over many weeks, paired with photometry that reveals a stable rotation period, plus thermal infrared estimates of surface temperature. If the path residuals wax and wane with solar distance and rotation as expected, the branch holds. If they persist in darkness or ignore spin phase, we look again. Branch 2 is porous, carbon-rich fragments. A competing view suggests that the traveler is a low-density shard from a dark parent body, where supervolatile ices can percolate through pore networks and emerge earlier than water would, producing a carbon-rich signature at long distances. Spectra with low reflectivity and gentle red slopes, along with a delayed appearance of waterlines closer to the Sun, would support this. It remains uncertain whether current data can distinguish a fragment from a more intact nucleus. What helps decide? Multiband spectra at several epochs, consistent color measurements, and a light curve that implies irregular shape rather than a smooth spheroid. Branch 3 is layered ices and delayed release. Evidence is limited, but one inference is that ices, stacked by volatility, can wake in sequence as warmth penetrates. Carbon monoxide and carbon dioxide respond, first, with water and other species joining later, while amorphous ice that once trapped gases reorganizes under heating and frees them. One possibility is that this staged chemistry explains both early activity and later changes without requiring unusual composition. What helps decide? Time-resolved spectroscopy that tracks the ratios of key lines across the approach and retreat, tied to models of heat flow through porous media with realistic thermal inertia. Branch 4 is rotation-driven plumbing. A minority view holds that the internal plumbing evolves as fractures open and close, and as dust mantles compact or loosen, so vents migrate across the surface and shift the direction of the net thrust. In this view, apparent course adjustments are the surface changing its own valves in response to repeated day-night cycles and seasonal sunlight on a tilted axis. It remains uncertain whether vent migration can be inferred remotely. What helps decide? Brightness variations that change their waveform shape over time, suggesting active source regions moving, plus any periodicities in spectroscopy that drift relative to the basic spin signal. Branch 5 is distant gravitational geometry. One possibility is that small, wide encounters with planets earlier along the path, though never close, set timing that makes today's trajectory look atypical until a longer arc is fitted. Resonant-like returns are unlikely for a one-pass interstellar visitor, but background tugs can still play a minor role. What helps decide? Orbit solutions that incorporate the full planetary system and test sensitivity to neglected terms, compared by independent teams. If differences shrink as models grow more complete, gravity and patience explain much of what seemed odd. Branch 6 is radiation pressure on dust. A competing view suggests that, for a time, The coma held enough fine particles that sunlight's push contributed a measurable, temporary acceleration that pointed away from the sun, then softened as the dust thinned. It remains uncertain whether the traveler's dust production is high enough for this effect to matter. What helps decide? Polarimetry and color measurements that constrain grain sizes, combined with brightness profiles of the coma to estimate dust cross-section, then folded into dynamical fits that include a radiation pressure term. Branch 7 is seasonal surface change. One possibility is that as the pole tilts toward the sun, a belt of vents sees longer, lower-angle light that sustains outflow through many rotations, then hands off to another belt as geometry shifts, creating a slow rotation of the thrust vector in inertial space. What helps decide? A consistent rotation pole solution from light curves, plus thermal models that predict which latitudes receive the most energy as a function of time, compared against epochs where motion residuals subtly change direction. Branch 8 is measurement and modeling artifacts. A competing view suggests that early residuals sometimes grow from uneven data quality, under-sampled rotation, or over-flexible model parameters that fit noise. The remedy is unglamorous and steady. It remains uncertain whether any specific anomaly rests here until independent reductions arrive. What helps decide? Shared raw data, documented calibration steps, and reanalysis by groups that do not share code or assumptions, followed by cross-checks against standards like star fields and well-behaved asteroids observed the same nights. Branch 9 is deep thermal re-radiation effects. Evidence is limited, but one inference is that uneven absorption and re-emission of heat by a dark, rough surface can create tiny forces that add to gas thrust in a fixed direction relative to the spin axis, analogous to well-known thermal recoil effects on asteroids. One possibility is that this contribution, while small, becomes non-negligible for low-mass, high-area-to-mass bodies. What helps decide? Combining thermal, inertia estimates with shape and spin to compute expected recoil, then checking whether adding that term reduces residuals without demanding unrealistic parameters. Branch 10 is brief dust outbursts. A minority view holds that short-lived increases in dust and gas can shift apparent brightness centers and momentarily bias astrometric positions, producing the illusion of a path change. It remains uncertain whether the traveler shows such events. What helps decide? High-cadence imaging to catch and time outbursts, plus using centroiding methods robust to asymmetric comae, and comparing positions from different instruments taken within the same hour to check consistency. Branch 11 is geometry that collimates gas. One possibility is that shallow bowls, ridges, and vents act like natural nozzles that narrow the flow, making each jet more efficient at producing thrust than a broad, diffuse fan would be. What helps decide? Indirectly, by tying repeated asymmetries in the coma's brightness to rotation phase, and by testing whether adding a small number of directional jets to the model reproduces both light curve features and motion residuals across several weeks. Branch 12 is the quiet null. Nothing unusual after all. A competing view suggests that once a longer arc is observed and better models are applied, the traveler's behavior will join the catalogue of natural cases that looked puzzling early and became ordinary later. What helps decide? Time, more data, and the willingness to retire a dramatic story in favor of a calmer one when the evidence points that way. This is not a defeat, it is a practice. Across all branches, two gentle rules keep the room tidy. First, tie each physical claim to at least one observable that can change with time in a predictable way. Rotation-linked brightness, distance-dependent gas ratios, or geometry-dependent thrust directions. Second, prefer shared archived data and independent fits, because agreement reached by different tools and teams is more restful than agreement reached by one. It remains uncertain whether any single branch will carry the whole story. Evidence is limited, but one inference is that several will cooperate. A porous fragment with layered ices and a tilted spin, releasing gas through geometry-shaped vents, with dust and radiation pressure briefly assisting, and early fits improving as data mature. That cooperation is how small bodies often speak. For listeners drifting towards sleep, the picture can stay simple. Imagine a ring of labelled paths around a small dark traveller. Each path is plausible, none requires raised voices. As nights pass, A few labels grow faint, a few grow darker, and the path we keep becomes the one that best fits the footprints the traveler actually leaves in the frost of starlight. In the next part, we will follow the implications outward in a gentle order: science, society, ethics, environment, before looping back for a soft reminder about humility and shared method. In science, the first implication of a careful reading of A Distant Traveler is improvement in our instruments and in the questions we ask of them. Coma models gain new terms. Thermal algorithms learn to treat pores with more patience. Survey pipelines practice holding longer arcs before drawing firm lines. One possibility is that observers will prioritize coordinated windows where photometry, spectroscopy, and thermal infrared overlap in time, so that rotation, chemistry, and temperature can be compared directly rather than in sequence. A competing view suggests that the largest gains will come from small, repeated acts of calibration shared across teams, where night sky flats, standard stars, and centroiding choices are documented with enough clarity that different groups can reproduce one another's results without guesswork. It remains uncertain whether the next interstellar visitor will be bright or faint, fast or slow, and that uncertainty encourages a culture of readiness rather than a chase for a single spectacular image. The second scientific implication is a better map of carbon in cold places. If layered ices truly wake in sequence, then a traveler's spectrum becomes a timeline, and timelines, when gathered from many objects, begin to outline where different kinds of carbon settled in the early building of planetary systems. Evidence is limited, but one inference is that a consistent early appearance of carbon dioxide, followed by water closer to the sun, would support models in which small bodies preserve distinct thermal histories. One possibility is that laboratory work with meteorites and analog ices will increasingly pair with remote observations, so the behaviors we infer at distance are grounded by measurements made under controlled light and temperature. A competing view suggests that new space missions with small, agile telescopes could park far from Earth's warmth and watch visitors in wavelengths that are difficult from the ground, turning faint lines into crisp ones and speculation into steady plots. In society, the first implication is about how we tell time together. When a visitor enters the news stream, classrooms and living rooms measure their days a little differently for a while, checking sunsets and shared links, listening for updates, and asking what has changed. One possibility is that museums and community observatories will build gentle, reusable programs around such events, with simple plots, a glossary on one page, and a practice of marking each claim as established, emerging, or open, so the public can enjoy the arc rather than only the headline. A competing view suggests that the most helpful response is even simpler: a promised update at a regular interval with no urgency in the language, so that interest has a steady place to land without spiking the pulse. It remains uncertain whether short videos, long reads, or in-person gatherings fit different communities best, which is a reason to offer all three when possible. The second societal implication is comfort with patient uncertainty. News cycles move quickly, while orbits unwind at their chosen pace, and bridging the two is a public skill we can nurture. Evidence is limited, but one inference is that when communicators model phrases like, "it remains uncertain whether," and "one possibility is," listeners learn to hold room for revision without feeling misled. A minority view holds that this language is not only kind to audiences, it is kind to researchers, because it sets expectations that new data may soften early impressions, a truth the sky teaches every season. The result is fewer disappointments and more durable curiosity, which serves both science and sleep. Ethics arrives as an unhurried companion rather than a judge, asking small questions that help large ones. If a world is scientifically valuable in its present state, how do we speak about it and measure it without disturbing what we hope to learn? Planetary protection offers clear guidance for spacecraft, and its spirit fits our stories as well. One possibility is committing to language that does not imply secret actions or immediate plans when none exist, because speculation dressed as urgency can steer attention away from the very observations that would settle the matter. A competing view suggests that ethics also asks us to consider equity, ensuring that the instruments and training needed to contribute to these sky-wide moments are shared beyond a few well-funded places, so that participation is global and benefits are widely felt. It remains uncertain whether budgets and policies will keep pace with that intention, yet stating the intention often helps it come true. Ethics also touches the boundary between wonder and worry. We can nourish wonder with accurate scale. A single small visitor, even if rich in gas, is a leaf on a wide river. The river keeps its level. When we say that aloud in simple terms, we lower the temperature of the room without cooling the curiosity. One possibility is that future guidelines for public communication will encourage explicit scale statements for any proposed effect, paired with timescales stated in years, decades, or longer, so that the mind can rest even as it stays interested. A competing view suggests that modeling exercises about far-reaching scenarios should continue, but should live in clear containers labeled as thought experiments, with ethics sections as standard as methods. The environmental implications thread two horizons. The first is local to Mars itself. If natural visitors add trace gases in amounts that are difficult to measure, then the lesson is about sensitivity, not transformation, and our work shifts to building long, stable records from orbiters and landers that can see tiny departures from seasonal norms. It remains uncertain whether such departures exist on present baselines. What helps is patient time series, because a sequence that spans many Martian years is the gentlest way to tell a subtle truth from natural variability. The second horizon is here at home, where the quiet study of other climates returns with gifts for understanding our own. One possibility is that radiative transfer models tuned for thin air and cold ground will sharpen our sense of how dust and ice clouds share the sky's work, and those insights can trickle into Earth systems science where appropriate. A competing view suggests that the practical gift is humbler, a public that has rehearsed what careful language sounds like when discussing planetary change, and so is better prepared to navigate complex findings without fatigue. There is also a tender implication for the night itself. When an object from far away becomes a brief companion, people step outside together, breathe the same air, and look up. That shared posture is an environmental act of its own, small, present, and good. Evidence is limited, but one inference is that gentle sky. Watching can renew attention to local horizons, to stars dimmed by city light, and to the value of dark, quiet places where the Milky Way is easy to see. In that sense, every visitor is an invitation to care for the conditions that let the sky be sky. We offer a late reminder that keeps the ground steady. Midway we placed a disclaimer, saying what is known and what is open, and near the close we place another. The branches we have explored remain possibilities until patient measurements settle them. It remains uncertain whether this traveller will teach us a new trick of porous ice, a new curve in thermal re-radiation, or only a better way to share data. One possibility is that its legacy will be procedural rather than dramatic, a finer cadence between surveys and follow-up, a clearer template for shared calibration, and a calmer public rhythm that welcomes revision as the sign of work well done. Before we dim the lamp, let a simple image hold the room. A small body turns in steady sunlight. Jets breathe on its warm face, then rest. Dust glows and settles. Gravity writes the long sentence. Our instruments copy the lines, sometimes with a shaky hand at first, then with greater precision as practice returns. Science grows from this repetition. Society learns how to listen. Ethics keeps the tone kind, and the environment receives attention that is patient and practical. In the next part, we will gather these threads into a quiet meta-lesson about humility, cooperation, and method, and then close the larger circle with a hopeful, sleepy outro that leaves both curiosity and comfort in good order. The pace will stay slow, the voice will stay even. There is time. Humility begins with scale. We are small compared with the distances we measure, and our instruments are precise but not perfect. One possibility is that treating every early curve and ratio as provisional, even when they look compelling, is the most respectful stance we can take toward the sky. A competing view suggests that audiences need confident answers, yet confidence can be quiet and conditional, expressed as here is what the data support today, and here is what would change our minds. It remains uncertain whether that phrasing will ever trend as strongly as bolder claims, but it builds trust that lasts longer than headlines. Humility also means remembering that a single traveller is a paragraph, not a book, and that patient context is a gift we give ourselves. Cooperation is the practical form of humility. No one team sees every wavelength or every hour of a night. Shared notebooks and open archives let different eyes and instruments correct one another's drift. Evidence is limited, but one inference is that the most restful advances arrive when observers agree in advance on a few simple habits. Publish the calibration steps, include the standard stars, post astrometry with uncertainties and codes, and tag spectra with times precise enough to match rotation. A minority view holds that cooperation can feel slow. The answer is rhythm, not rush regular updates that keep everyone moving together and leave few surprises for review. In that rhythm, amateurs and students find natural places to contribute, and their contributions lengthen arcs in ways large telescopes cannot. Method, in turn, is cooperation formalized. We set thresholds before we look. We write down which tests would count as support for one branch over another. We mark hypotheses with signposts, so our words carry their status in plain language. One possibility is that journals and preprint servers will increasingly welcome brief, high-quality negative results, because a careful, "this did not hold up" closes doors that others might spend months trying. A competing view suggests that incentives still favor novelty. Method answers by giving novelty room only when checklists are met. It remains uncertain whether culture or policy will lead this change, but bedtime science can model it tonight. Clarity first, and then possibility, within sight of the ground. Humility also lives in timescales. Changing a planet is slow in ordinary physics, while changing a mind can be fast. So we repeat the soft disclaimers near our close. The observed path deviations still fit within natural explanations that combine outgassing, sunlight's push on dust, and long geometry. It remains uncertain whether any residuals will persist after long arcs and improved models. If they do, we widen the circle of measured forces before we widen the circle of claims. Evidence is limited, but one inference is that layered ices and porous matrices can easily mimic early signs that looked unusual at first. A minority view holds that a future case may strain our current boxes. If that day comes, these habits, sharing, predefining, labeling, will be the tools that help us judge with care. Cooperation also means shared ethics. We speak about other worlds in ways that protect their scientific value, and we speak with one another in ways that protect the patience we need to learn. One possibility is to keep a simple practice. Whenever we name a possibility with large cultural weight, we place a calm sentence beside it, noting what would count as evidence and how far we remain from that threshold. A competing view suggests that such sentences drain drama. What they truly drain is unnecessary arousal, making room for a steadier curiosity that serves both learning and rest. Method finally returns as kindness to attention. At day's end, most listeners carry full lives. A 7-point checklist, a glossary with one-sentence definitions, and a map of branches that shows where data stand today. These are tools that welcome anyone into the room without hurry. It remains uncertain whether this traveler will bring a spectacular surprise. It is certain that using these tools will leave us better prepared for the next one, and that preparation is its own quiet reward. If you are drifting now, let the last, simple shape hold your thoughts. Imagine a modest workshop with a large, clean table. On it are a few well-used instruments, a shared notebook, and a map of the sky with soft pencil marks. People come and go, add a line, erase a smudge, and leave a note for the next shift. The traveler moves on. The map grows clearer. The notebook fills not with proclamations, but with careful entries that make the work easy to trust. That is humility. That is cooperation. That is method. In the final part, we will tuck these pages away with a hopeful, sleepy outro, a soft invitation to care for the night above and the questions that live there. Settle your breathing into an easy rhythm while we gather the room. A small traveler came in from the dark, and together we practiced a way of seeing that is soft on the ears and steady on the mind. We kept a simple map of possibilities. We marked our steps with clear signposts, and we let time, not urgency, decide which branches to keep. The sky did what it always does. It offered light and motion. We did what we can do at our best. We answered with patience, cooperation, and care. Before the lights dim, let a single picture hold us. Imagine a quiet shoreline at dusk. The tide is low, and the air is cool. Far out, a dark shape crosses the band of water, not rushing, just moving with its own inner clock. On the sand beside you lies a notebook with notes from people you will never meet, a time, a brightness, a few measured lines, and a sentence that starts with one possibility: island. You add a line of your own and close the cover gently. The work is shared. The mood is even. The night welcomes such company. We can leave with 3 soft lessons. First, facts first. When the evidence is clear, name it simply and let it stand. Comets outgas, rotation matters. Thin air on Mars is mostly carbon dioxide, with a surface pressure far below Earth's. Gravity carries almost everything we see, and sunlight adds a most delicate push that matters, only when counted over many turns. Keeping such anchors near at hand is not merely accurate, it is restful, because it lets imagination float without losing the shore. Second, speculation can be kind when it is transparent. One possibility is that a porous, carbon-rich fragment wakes in layers, the gentlest gases stirring first and shaping the smallest turns in a long path. A competing view suggests that early ratios soften with calibration and angle, joining the familiar patterns in our catalogue. It remains uncertain whether this traveller will leave any stubborn residues in our models once the observing arc is long, and that uncertainty is gentle rather than sharp when we speak it plainly. Evidence is limited, but one inference is that clarity of language, those small signposts, does more to comfort and to teach than any flourish ever could. Third, cooperation is a quiet form of trust. Wide sky projects live on shared calibration frames, on standard stars observed with care, on photometry that lists uncertainties, on spectra tagged with times that match a rotation within a fraction of an hour. The habit of posting both what worked and what did not is a gift to strangers and to your future self. One possibility is that the legacy of this visitor will be a more practiced rhythm of coordination between survey telescopes, follow-up spectrographs, and orbiting thermal eyes. A competing view suggests that the deeper gain will be cultural, a public and a research community more at ease with phrases like "it remains uncertain whether," and a little less hungry for conclusions that arrive too soon. There is room here for gratitude. Instruments kept their watch under clear and cloudy skies. Teams compared notes. People with busy days stepped outside for a few minutes and remembered that there is more above them than ceiling and cloud. When this happens, the boundary between science and society softens in a lovely way. The same words that calm a classroom can calm a living room. The same plot that persuades a peer reviewer can reassure a parent. Quiet science language has this power. It lets many lives sit beside one another comfortably. We also set an ethic in the middle of our story, and we can set it down again with care. We do not rush other worlds with our claims. We protect their scientific value by keeping our phrases modest. We recall that thin atmospheres breathe with their seasons, and that a single small visitor, however interesting, is a leaf on a large lake. One possibility is that long, consistent records from orbiters and landers will one day show tiny, seasonal fingerprints from passing objects. A competing view suggests that the signals will drown in the planet's own rhythm, and that the lesson will be about sensitivity rather than transformation. Either outcome is helpful, both are calm. As the lamp lowers, we offer a second soft disclaimer near the end, matching the one we placed at the midpoint. What you heard tonight blended established measurements with well-labeled possibilities. The established pieces rest on widely shared data and long practice. The possibilities wore their signposts, so that your mind could stay settled, even while it wandered. If later observations revise a number or retire a branch, the method does not fail. It succeeds, because clear language leaves room for revision to slide into place without friction. If you would like a small practice to carry into sleep, try this. When a new claim about the sky comes to you tomorrow, invite it to sit down and ask 3 gentle questions. Which part is measured? Which part begins with one possibility is or its siblings? What observation would most kindly decide between branches? You do not need to be a specialist to ask these. They are human-scale questions, and they keep both curiosity and rest in good order. Now the final picture. The traveller continues on, and gravity writes the long sentence of its path. Somewhere, a student points a small telescope and learns the star field by heart. Somewhere else, a researcher checks a calibration file one last time and uploads the data with a note. A family walks home from an evening errand and pauses to look up, not quite sure which point of light is which, and still happy to have looked. In all of these small scenes, the same quiet mood is present. It is the mood of shared attention, humble claims, and careful craft. It is enough. If you prefer, you may leave a soft note in your own mind, the city or village where you listened, the local time when your eyes began to grow heavy, and then let the note fade. The sky will still be there in the morning. Your questions will wait in the same notebook. The pace can remain slow. Sleep well now. Let the room darken and the breath lengthen. Somewhere above the roofline, a modest traveller turns in sunlight that has crossed a long distance to arrive, warms one face and then the other, and leaves a faint, true trace that patient instruments will follow. We will meet it again in calm plots and careful pages, and we will learn as much from the pace as from the result. Good night.